Welcome, everyone. My name is John Dunn. I'm from AWR, and I hope everyone's having a good show. What I'd like to talk about a little bit today is EM technology, of course, in obviously reference to our software. But more than just showing you some features of EM, what I really want to get into is an entire philosophy of where we see EM simulation tools going. Okay, so without further ado, let's get going. In this slide, what I've attempted to do is encapsulate the world of EM simulation for the average circuit designer. Now, I have to emphasize circuit design here. This is for people on PC boards, modules, MMICs, silicon chips. I'm not talking about people doing antennas on F-16 airplanes, F-22s, whatever they are now, urban propagation path problems. These are automobiles. These are important problems, but they're outside of my domain of discussion, okay? And of course, our company focuses on these circuit simulators. So let's think of EM in the world of circuits, all right? Now, what you see in this slide, I've attempted to show you a classification or taxonomy, if you will, of the major types, classes of EM simulators. I'm sure many of you know this already. You see three bubbles going across with a small gold bubble below. So let's run through this quickly. And the reason I'm doing this is we're trying to learn from this picture historically what's been happening with EM and then predict the future, okay? So that the argument I'm going to use here is that these trends will continue. We have to identify the trends and see how they continue, okay? Now, the vertical axis is computation time. Of course, in general, the more complicated the problem, the longer it takes to solve. The horizontal axis is how general the geometry is. These are, quite frankly, marketing terms. By 2D simulator, the pink bubble, cross-sectional solvers, what I mean there are solvers that would just take the cross-section of your transmission lines. Think of two coupled lines. It takes the cross-section. It does an EM solve for the line parameters, RLCG. You have the length, of course, from what you plunked down in the schematic, and you're done, okay? And we'll talk more about those in a minute because of the history of them. The second group is the method of moment simulators, sometimes called 2.5D, 3D planar. I'm sure many of you are familiar with them. Been a workhorse for years. The biggest bubble, quite frankly, they're the most commonly used simulators in circuits. And there's a good reason for that, because circuits are planar, okay? The third bubble, way on the right, 3D methods. These would be the finite element methods, the boundary element methods, the finite difference time domain methods, the finite integral methods. You know them. They're all around the show. The advantage, very general. The disadvantage, they're slow, right? Because it's more general, you have to mesh more. There's no magic there. If we had something that could do a shape more general faster, guess what? You'd all use that, right? There would not be three bubbles, okay? That's the reason you have different bubbles. Things are more specialized, but therefore faster. There's two other things I want to point out in this slide. Notice the purple dashed oval, and it says 96.2%. Incidentally, that number comes from careful market analysis, of course. 96.2% of a circuit is here for MMIC module board. When you guys are doing your EM simulations out there, on your boards, your modules, your circuits, guess what? They're mainly planar circuits. That method of moments bubble is going to get you a long way, okay? The reason they're planar is they can make them. They call it photolithography. They call it e-beam machines. If we don't have planar circuits, fundamentally, we're not in the world of circuits as we know them, okay? So take advantage of it. I'm constantly amazed at people who throw a full 3D moment or a finite element method at a via. Why? You can do it in a planar circuit much faster, many more of them. It's not 100% planar. So that bubble, that 3D method bubble is there. There are gaps in dielectrics where you put the chip down to the ground plane. There are bond wires. There are SMA connectors. There are probe tips. There are 3D objects, and you need 3D. So I'm not saying you don't, but I'm saying a lot of the world is planar. Okay, and the final thing I want to point out on this busy slide, and this is going to be our theme when we go back in time, which we're about to do. Notice the gold bubble says EM models, bond wire spiral inductors. An EM model is something that uses EM, but you don't even know it's using EM, and I'll come back to that theme. So let's go back in time here, and two characters. And basically what these say is, you know, if you look, why don't you look back in history, because it's kind of going to happen again as we keep going. That's our theme. So let's take a look. Before we do, I have to give one caveat. I've been saying chips, boards, modules. In chip technology, we have two very different kinds of chips. We have 3 5s, gallium nitride, arsenide, indium phosphide, etc. Tends to have not many elements, tends to have a really good ground plane, you know, 100 microns of gas, great ground plane. Very different than silicon chip technology. No well-defined ground plane. Zillions of nets, okay? Large amount of metal. They both use EM, but very differently. When I'm talking about the tools I'm showing you in the future, I'm going to be 95% on 3 5s. Gas, mimics, gallium nitride. Few devices, fair amount of interconnect, spirals, etc. Nice ground plane, that sort of device. High enough in frequency, you need high frequency EM tools, S parameter based. If you show those tools to a silicon chip designer, there's about one place they're going to use them, and it's a spiral. Everywhere else, they're going to do lumped parasitic extraction of the nets, pretty much. So it's an important world. It's EM, but it's not my focus today. Okay? The other caveat I want to make where we use EM, board module, I'm not going to talk about power plane simulation tools. Important problem. I'm talking the interconnect, spirals, vias, etc. Okay? Okay, the year's 1990. We were all younger, some of us much younger. I had hair. I was thinner. I had hope. Okay? And in those days, 1990, when these tools came out, here is what you did with them. If you look on the right slide, planar EM, your moment method, you know what we did? We did T's, bends, and crosses. And it was so exciting because we didn't need a model from the literature. And you, as a designer, you could simulate these guys, and you came up with your little library of little S parameter files, and you had a discontinuity model with S parameters from EM. And that thing cost you $40,000. And you could do what you're seeing there. You could do a T, and it took about a minute or 2 minutes of frequency point. And that's what we did. And yes, we had finite element methods. As a matter of fact, HFSS, Zolsendis, et cetera, that had come out. And I should mention in steering planar EM, hats off to Jim Radio, Sonnet, one of the first people to commercialize moment methods, Zolsendis, finite element methods, and Ansoff. And you know what you did in HFSS? You did one via. You did one BGA ball. And it took about 5 or 8 minutes of frequency point. And we would draw these things, and we were all happy. Remember I had mentioned in the previous slide that cross-sectional solver, which I said we solved the line and we got the parameters. We had those. They were very exciting. They were separate tools. You bought these things. You would actually spend $1,000 to get a cross-sectional solver, and it was great. You know, and you'd put in your embedded microstrip line, and everything was just glowing gloriously. Then people, things like IEEE and stuff, people came out with free versions, and you download your little free version, you know. And they were standalone tools, and you draw these things. The world of silicon, not my focus. They were counting squares on the interconnect, and everything was capacitance, right? Okay, let's go to the present. 3 5s. People now, like with our planar simulator, for instance, with the fast solver technologies that are out there, we can basically do all the interconnect on a MMIC, typical MMIC. You see, I think it's a 2-stage MMIC there. We can do all the interconnect on that entire MMIC in about 40 minutes, all of it. We do not worry about one T-junction, okay? Modules. You cannot, it depends how complicated the module is. You are getting in the world now where you can do an entire simple module. Few ground plane layers, few signal layers, etc. Okay, silicon, not my focus. Tools have gotten more expensive. And here's the point I want to make at the lower right of this slide. What happened to those cross-sectional solvers? I said people paid money for them. You get them from IEEE. It was a big deal. They're gone. They don't exist. The answer is that you use them every day. Every time you fire up an EM circuit simulator and you plunk down a transmission line, it has a model. And in at least in our software, and it's true of our competitors too, I'm sure, that model is EM. It does the cross-sectional solve. You don't even know it's doing EM, right? It's totally hidden from you. You have no idea what the method is unless you're an EM nerd like me. Okay. It happens to be a moment method, but the point being, that's why it's an EM model. Model implies I plunk it down, it gets me the answer, I don't care how, and it happens to be EM. So what we're seeing more and more is the world of EM models. The 96.2% is becoming EM models. You use them. You don't have a great idea of all, you're not studying Maxwell's equations for 6 years, wondering how many modes should be on the port. It just does it. Why can we do that? It's planar, it's limited geometries, they're well studied. When in our software you plunk down a T model, it's EM, okay? We have EMT models. You don't really care how we got it. We simulated all the EM, got it all done. You're going to see this more and more. The gold circle at the bottom, we have the bond wires. You can put bond wires in our software. It's really EM. It's a moment method code. They take the EM wires and chop them up. Do you really care about those details? No. So the big theme we're seeing here is as the computers get more powerful and sophisticated, yes, you can simulate a bigger problem, but for most of you, a lot of your EM you are doing, you don't even know you're using EM. When you put models down on that schematic, it's all EM. So where do you think the trend is going to be? It's going to continue and continue. Easier to use, and quite frankly, our dream at AWR is to get you to use EM, and it's so automatic, you barely even know you're using it. Okay, so here's an example from our software, and you are seeing a MMIC on the left, bond wired over to a module. That's an LTCC module. The point being, what you can do, what we're trying to do now, is when you need to EM something. So you got the built-in models most of the time, but when you literally don't have the model and you need to EM it, it's essentially one button click. You've got this stuff drawn already. You're plunking down models, they have layout, they're there. Why on earth are you going out to a 3D simulator, drawing all the shapes and all that? Wouldn't you rather just click the button? Sure you would. With the click of a button, you can send it to the planar like that spiral axiom. Notice the bond wires, we can ship them off to Analyst, which is our 3D finite element simulator. Everything in the environment, ease of use, transparency. The 3D Go to the next slide, actually. Okay, here's another example. This is our finite element simulator done in our software. If you're used to these things, let me point out a couple details that, again, ease of use, transparency, not worry about the details. You see port 1 there on the left? That is a line on a board coming into a transition up a BGA ball onto an interposer, a module, bond wire to a chip. Port 1 is a wave port. If you're used to finite element methods, very standard, you put a wave port on. And what do you have to do when you put on the wave port? Number of modes. What kind of impedance definition? Draw the impedance line. You know all this stuff if you're worried about it. Guess what? When you're doing circuit simulations on boards, it's almost always the same setup. So in our software, you draw the line over, you go, it's a port, you're done. Automatically a wave port, impedance is right, number of modes has been figured out, you're done. We can do that because you're always in those types of environments, okay? If you're on your automobile, I can't do it. Let's go to another one. Same example. How did they draw those balls? They didn't. They never drew them. What they did, and you can see on the left a little, this is a window where we put the symbol of what we call the P cells. Those have already been drawn, and you just throw them in, and you can set little parameters for the number of them and size and width, but they're pre-configured. I mean, why are you drawing those dumb things? They're pre-configured P cells. Okay, on and on like this, ease of use. This shows you the P cells with the bond wires. You're not drawing it. You're plunking down a cell on that window. It draws it. You can see the, if you want to diddle around with the shape, go for it. But again, the last thing you want to be doing is drawing a lot of this. Another thing you can do very quickly, the simulation region. Notice here the person has their entire layout, which is hooked up to the schematic in the models. They only want to simulate this input path. Notice the boundary of the finite element method simulation is only drawn around part of the circuit. You don't want to draw the whole circuit and have to chop it out. You can just do part of it. You add on the ports very quickly. You can see the mesh there from just part of it. Incidentally, we did mesh the air. I'm not showing it because it would look confusing. So the air was meshed. I just hit it. Okay, I already mentioned the ports are automatically added. You can see on the right, that's a circuit port hooked off the bond wire. Okay. Another thing we can do in the circuit simulator is hierarchy. Why on a schematic do you use subcircuits? You can reuse them, etc. And what happens in the layout? You have subcells. You draw that inductor once, can keep reusing it. In this circuit, they have a chip level, a board level, a module level. With hierarchy, you can keep building up the layout, then EM simulate at whatever level you want. Okay, again, very easy to use, same as the circuit flow. So in conclusion, if we look at history, we're seeing a couple trends. I'll start with the second point. EM models are becoming more and more prevalent, and what EM model means to you is you don't even know you're using EM. Okay, and you're seeing it more and more. A lot of you use EM every day, and you go, no, I don't. Yes, you do. Use a transmission line model, you're probably using EM. Okay. The second thing we're going to see is EM more and more tightly integrated into the circuit simulation environment because you guys are doing planar circuits. That's your world. Okay? And he's not. So if you're doing antennas on automobiles, yeah, you can't do this. You'd have to be drawing your automobile, etc. Okay. For the rest of you on modules, boards, MMICs, planar patch antennas, okay, etc. It's your world. Now, I'm going to conclude. I'm out of time. Please drop by the booth. And the new exciting development that we're bringing out this fall is what happens when you need the SMA connector. Okay. In the new release of the software coming out this fall, we do have a full 3D editor. So when you need the SMA connector, when you need that probe tip coming down at an angle and you got to draw it, you can now do it in our software. It hooks right up into our main circuit simulation environment, and you're good to go. And I'll conclude with this. If you do it a lot, you can even make a P-cell. It's in your library, and you can reuse it. Thank you very much, everyone. Please come by the booth. And also find out about the party. We have the best party at MTT, so we're right over there. Thanks a lot. Have a great show.